So we started off, we did the limit definition to find the slope of y equals 5 minus 2x at x equals 4. And we discussed just a second ago, after we solved this out, that you knew the answer before I told you to work it the hard way. Now, thinking about what this says, when you solve it out and it says f prime of x equals negative 2, how is that different from the problems we've done up till now? Say that again?
We've always been left with an exponent.
A variable. Yeah, we've always been left with a variable here. Here we're not left with a variable. What do you think that signifies when we see that we're not left with a variable here?
The slope's the same at every point.
It's the same at every point. The x value does not matter. It does not matter what my x value is, my slope is always negative 2 on that line. Where when we did the parabola using the limit definition of the derivative, and we did square root, so forth, using the limit definition of the derivative, we always had an x value in there because the domain value affected what the slope was, because the slopes were constantly changing. Does that make sense? All right, but here it's not. Now, let's look at the graph of this real quick before we go further. All right, so we've got f of x equals 5 minus 2x. So we've got a y-intercept of 5 and a slope of negative 2, right? Mm-hmm. We better. It's a line. So we're here. Now, this is the graph of, and I call it y, but I'll say for the purposes of this graph that's f of x. Now, when I come here and I trip over that mat, I graph its derivative, and its derivative is negative 2. That is the graph of f prime of x. So what this is doing is this is matching, this is the graph of the slope of this function. The graph of y equals negative 2 is this line here. So whatever my point is on this line, it just happens to be the slope of this line.
That's what I was talking about.
Now, let's go back to one we looked at the other day. What was and I don't have them written down, what was the first parabola that we looked at in class? It was the first example we did.
It was
Minus x plus 5? All right, and when we solved it out, what did we get that the slope was? And I'm going to call it y prime. 2x minus 1. All right, well, we look over here, and the graph of x squared minus x plus 5. Let's talk about what this graph looks like. Let's do an xy table here. So let's start with negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. All right, the two of you do negative 4. Y'all do negative 3. Y'all do negative 2. Y'all do negative 1.
so we both do negative 4.
Yeah. Y'all make sure y'all agree with each other. 0, 1. The three of y'all do 2. Y'all do 3. You do 4. So we're plugging. So I want to know the y values for it.
Yeah.
Not the slope values, but the y values.
Ooh, okay. We didn't do it right.
So you're plugging in negative 4 here.
25.
All right, so this is 25.
We have to jump.
All right.
I said imagine we're both wrong.
All right, what about negative 3?
17.
17. Negative 2. 7. Negative 1. -3? 0? 5, all right. 1? 5? All right, something's not right in here. Okay. 2? 7? 3? 11? 4?
That makes sense.
Oh, you're right.
17?
Yeah. See, okay. You're killing me.
That makes sense.
Okay.
I got that -2 value wrong.
All right, what is it?
9.
9? Not 11?
We're supposed to use the top one, right? Yeah, the top one. Here, you know.
6 plus 5 is 11.
All right, we're using this line. We're graphing the parabola. We're graphing the parabola. What is -2?
11.
dead.
11.
Have you genuinely freaking out? I'm freezing.
What is -1?
7.
7. All right, this is better.
No, no.
This is better.
It's 7.
Oh, wait.
It's
Never
7.
mind, I did it wrong.
Again.
I did the wrong number again.
2 wrongs didn't make a right, did it?
No.
Okay.
We got it.
Are we okay to keep going? I'm not sure I am. All right, so here we are. Let's look at this graph. So -4. I'm gonna go up 25. That looks like about 25, doesn't it?
Sure.
5,
Yeah.
10,
Right.
15, 20, 25. All right. So back 4 up 25. Back 3 up 17. Put me about right there. Back 2. Oh, this is horrible. I'm gonna lose my art credentials.
Wait, how is it already off 11? I thought it was always 4.
Okay. So let's put it here. Here. All right. Back 2 up 11. Be about right here. Back 1 up 7. 0, 5. And then 1 was 5.
And then
2 is 7. 3 is 11. And then 4 was 17. All right. So, oh, this is the most atrocious parabola ever drawn. All right. So, I didn't even come close to the dots. All right. Anyway, now,
plot the points.
what now?
Why'd you plot the points if you were just gonna draw a line?
It's a parabola. That's not a line. That's a parabola. Critical. I practiced this all last night trying to get it right. Get it criticized. All right. Okay. Before we get off topic. All right. Now, this is the graph. Now let's look at the graph of what we call the derivative of this. So it's 2x minus 1. So we have a y-intercept of -1, right? We just put it
Yes.
about right there. And we have a slope of 2. So it's going to be here. So it's going to look something like that. Now, this is what I want you to take note of. Everything where this orange line is below the x-axis represents a negative value for the orange line, right? And what does the orange line represent? The derivative. So any negative y value for my derivative is saying that the original function would be decreasing there. And it is. Now, this value's going down, right?
Yep.
So this may be -20, where this may be -10, and so forth. But if you think about it, these values out here on the parabola are steeper than these values in here. So the closer our graph of our derivative gets to the x-axis, the less steep the parabola is. Whether it's steep in a negative direction or steep in a positive direction, yes.
Did you?
I didn't mean to go through the vertex. That's bothering you, isn't it?
What'd you say?
That I went through the vertex.
Oh, no.
Okay.
No, I think that line might not be right because you're going by increments of 5 on the y-axis and not by 1 like you are on the x-axis.
Man, I got some critics in here. I tried doing a slope of what would be essentially 2.
Okay.
And-
I was just trying to figure out
Yeah,
if it was.
yeah, it's not perfectly accurate. I understand.
Not sure.
Yes.
Is that point significant?
Which point?
The point where the derivative graph crosses the y equals graph. Like,
Okay, we're at the point where the derivative graph crosses this. This
Yeah.
should not be at the vertex.
but like, is that a significant point? Like, in
Well,
general?
it's where the derivative equals to the function. We could solve it out by setting this equation equal to this equation and get the answer. It's not relevant to the graph, but if you're bored, you might
No.
think that would be neat to solve. So, but no, that point is the point that's of significance is the x-intercept here should correspond with where the slope is 0 on the parabola. Does that not make sense?
No.
Okay. Everything from here and above on the orange graph is positive, right?
Yes.
Okay. Which would mean that should be where the parabola is increasing.
So the vertex is the point where the
Slope is 0.
slope is 0.
Yeah,
Okay.
because think about it. You're going from negative slopes to positive slopes.
So like,
So
how would you just plug in 0 to the derivative 1 to find the vertex?
to find the vertex? This was a good question. How, are y'all listening? How, based on what I have on the board, would be the best way to find the vertex? What do you think?
Find where the derivative function is equal to 0.
Find where the derivative is equal to 0. What do y'all think?
I think that's a good idea.
That's correct. So, we would have 2x minus 1 equals 0. So 2x equals 1, so x equals 1/2.
So that's where the vertex is.
That's the x coordinate of the vertex.
And then the y coordinate, you can plug in the 1/2
To where?
to the top.
Yeah.
coordinate.
So we find the x value of the vertex. To find the y value of the vertex, we don't plug back into here. If we plug back into here, we get 0. We go back and we plug back into the original equation. And that would give us the actual point. Yes?
Why did we use the derivative thing to solve for the x value of the function's
Okay.
vertex?
Well, we didn't have to. We could do negative b over 2a, and that would give us the same result. Negative b over 2a is a way you can find the vertex of a parabola. Negative b is negative 1, right? So the negative of negative 1 is 1, and then over 2a would be 1/2. Now, the proof behind that is done in completing the square with this,
That's just more complicated.
but this is just using the fact that the vertex of a parabola is the only point on the parabola where the slope is 0. So that's the reason we did it. We were using the context of the slope being 0 to find it, where here you're using, let's take this and let's put it in y equals x minus h squared plus k form. It's whatever. I mean, that's just two different ways to find the same point. Good question. Yes?
So if it was a parabola with like a hole at the vertex,
It wouldn't be a parabola.
well,
Parabolas are continuous
if
functions.
it was that with a hole,
Okay?
then at the vertex, then like,
If you
Would you
graph
do
its
the same-
derivative,
would you do the same thing that you did with like the tables to find the value?
that would be one way. But you're not gonna run into that.
Okay.
But, I mean, if you had a hole here, then your derivative would also have to be undefined there. And the only way we could really get to that is by using a piecewise function. So the derivative would also be a piecewise function.
Okay.
Any other questions? Yes.
Could you not achieve that by like a removable discontinuity? Like multiply the numerator and the denominator by x of a second.
All right,
order polynomial?
you said that. Could I do that? What is
Sorry,
that?
Sorry, a hole at the vertex.
Okay.
Like,
There's not a hole at the vertex
I know,
in this problem here.
I know,
All right.
but I was offering a way
Okay.
I thought you might be able to do it without a piecewise function.
So what are you saying?
Like so for x squared minus x plus 5, if you multiply the numerator and the denominator by x, then there will be a hole at 0.
X squared minus x plus 5 if I divide by x? Is that what you're saying? If I divide by
Multiply
x.
the numerator and the denominator by x, or by whatever you want, and you can put a hole anywhere. By x minus 5.
Well, all right, technically you can't do that because you would have to establish, if I'm gonna multiply this by x over x, the only way I can do that is if x does not equal to 0.
Well, yeah, I know it would be a new function, but I was just saying that you could, like, as an expression, you could make an expression that.
All right, that's one thing that should be cleared up when you're doing just anything with rational expressions and you start multiplying by stuff. Like if you're solving for x, this is algebra. X minus 8 plus 3 over 4 equals 8. Let's just say that's your equation you're wanting to solve for x. And you go through and you multiply every term through by the least common denominator. You multiply by 4 times x minus 8. Well, hold up. You multiply, that way all your denominators go away. But the only way that you're able to multiply by that is to assume that x minus 8 is not 0. But since you're solving for an equation, if you solve this equation and you get x equals 8 as your solution, then there is no solution to the problem. So that kind of kicks its own self out.
Is that extraneous? Is that what that?
Extraneous, or yeah, a restriction is another term for it. There are a lot of things in algebra that kind of you don't really talk about, but they're there. But no, we cannot just go through and multiply by an x over an x, because there is a chance that x could equal to 0. So we have to establish, if we're going to do this to change it, we'd have to say that if x does not equal to 0.
If you were like intending to design a new function that had a hole at the vertex, that was what I was imagining doing.
If I were going to design this so there was a hole at the vertex, I would say my function is f of x equals, no, the hole here would be at 0.
Yeah, I realized that was a mistake.
Okay,
But
okay.
Just, you could put it wherever the vertex was by just saying x minus.
I'd have to look at that later.
Okay.
All right. Now, give me a second. Let me find my eraser. I guess you could multiply it by 2x minus 1 over 2x minus 1. But again, you'd have to establish that. But now it's not a polynomial equation anymore.
Right.
But it would, I think it
But
would be
you
a
have to do it
graph.
piecewise
Yeah, I think
to
it would be.
accomplish that same
Yeah.
result.
Yeah, I think that's right.
Mr. Round,
Yes. Who said something?
friend Steven. Oh, I was telling Lydia.
All right, anyway, let's get back to this. All right, so I think we introduced this problem last time, the limit as h approaches 0. And we were talking about f of x plus h minus f of x all over h. Is someone at the door? Okay. So go ahead and set that up with the limit definition of the derivative.
That is
Oh yeah, I know that.
Oh, 1 over x. I'm sorry, f of x equals 1 over x. Yeah. And I just want the general derivative of this. F of x equals 1 over x. Did we talk about this problem last time? Okay. Yeah, that's right.
Goes where it approaches. That makes so much more sense.
0. Thanks for asking. I understand why you couldn't read that. All right, did y'all get that? Okay.
No. I don't understand how to plug it in.
Well, yeah, I did get that.
All right, this is f of x plus h. If I gave you this and I said, what is f of 3, what would you tell me f of 3 is? It's 1 over 3, right? If I said, what is f of smiley face, you would tell me it's 1 over smiley face, right? Well, what is f of x plus h? It's 1 over x plus h. So for the f of x plus h portion of the formula, you plug in that.
One over eight.
All right, any suggestions of where to go from here? Yes.
Subtract those. Make them like terms and then subtract them.
Okay, how do we make them like terms?
Yes.
Thanks, Stephen.
X plus H.
Yeah, you're not, if you're solving for x,
Times-
you could have equals and cross multiply, but
No.
we can't
X
just
plus
cross multiply.
H. Put that in the denominator of the other one, times X
Okay.
plus H on top.
Okay, so
And
multiplying
then-
by 1. So we got x
Yeah.
over x times 1 over x plus h. Minus 1 over x times x plus h over x plus h.
Yes.
All over
H.
h.
Wait, is that not the same thing as cross multiplication?
No.
Oh.
No, you're multiplying by 1. Cross multiplying is when you have two fractions equal to each other and you're trying to solve for x.
Oh.
So
It's the same principle, but if you cross multiply,
Yeah.
yeah.
You
All right.
don't end up doing the.
You're usually trying to eliminate your fractions at that.
X over. Oh my goodness.
No, it's a 0, not a no.
You multiply by the reciprocal whenever you're dividing, right?
We can multiply by the reciprocal next. All right, let's clean up the numerator
Yeah, I was
first.
about to
What does
say-
it become?
H.
Just h?
Yeah.
Be careful.
Negative H.
So I've got negative h over x times x plus h, right?
Yes.
Times 1 over h.
Okay.
Mhm.
So
So,
No.
is correct?
no. that how you do
Negative 1 f prime of x equals the limit as h approaches 0 of negative 1 over x times x plus h.
Do we need to do the bottom, like multiply it?
Well, what happens when we plug in 0 for h now? Do we get 0 over 0?
No.
No, we don't, do we?
No.
What do we get?
1 over x squared, negative 1 over x.
Yeah, we would get, so f prime of x equals, I'm gonna do this in 2 steps. Negative 1 over x times x plus 0, right? Which would be negative 1 over x squared. What does the graph of negative 1 over x squared look like?
You mean,
1 over x looks like this.
So it'd be, so is it like flipped where they both
It's like
point in the
this.
same direction?
Yes. Is that what you're saying?
Yeah.
That's beautiful. It's like
Good
you're
job.
directing a choir.
Thanks.
Okay, anyway. All right, so let's graph it in orange. Let's graph this in orange. Well, and now it's not going to be 100% the same thing, but it's going to look something like this. Does that make sense?
Yes.
Why?
Yes.
Why does that make sense?
Because we just did it.
Because
the other
you
thing.
can't.
Say that again.
It was not very well said. It's going the negative direction.
All right, don't use the word it. You said it is going in the negative direction. What is it?
The function is going in the negative, the derivative.
Okay. All right. What are you saying, William? Yeah, no?
So don't call them.
All right, Reuben.
So because x is squared, there can't be a negative in the denominator. So all the y values have to be negative y values.
Yeah, because it's negative 1 over that, right?
Right.
Okay. But think about what else it's saying here.
The,
Yes.
the slope of the green graph
The slope of the green graph.
is going, it's going negative. And
Alright.
then it's going negative to positive. And that's how the derivative is going.
The green graph is always decreasing, correct? It decreases, it decreases. So if the green graph is decreasing, the slope of the green graph everywhere is
Negative.
negative. So all my derivative values should be
Negative.
negative. And on top of that,
It's also like,
we're really steep negative right here, right?
yes.
On the green graph, so on the graph of the derivative, we get very low values for negative values. So, now, for homework, what I want you to look at, not look at, I want you to do. You just told us to look at it. All right, on the 3, I figured if anyone could handle that, you could. So on 3.1, let's do question 1.
All of it?
Yes. Question 2. Now understand some of these notes that are written in here. This was my textbook when I was in college.
It's just got some room in the circle.
And then let's do the odd problems. Not the odd problems. Let's do the circled problems 3, 4, and 5. Don't do 8, 9, and 15 yet. We'll talk about those later. So,
1, 2, 3, 4, 5, 6, 7.